Welcome to the Terran Space Academy. Please don't forget to like and subscribe. Tuition is voluntary at patreon.com/Terran Space Academy. The success of humanity's expansion into space is dependent upon affordable access. As long as it costs more than $1,000 per kilogram to get into space, true space development will be hindered. To solve this problem, Elon Musk has been building this, the Starship. I'm sure you've all seen the beautiful flight and rather hard landing of serial number 8. Let's see what we can learn from this dramatic test flight. Here we see the Starship waiting to launch. Let's evaluate a few statistics. It has a dry mass of 120,000 kilograms or 120 metric tons. It will need enough fuel in this flight to achieve an altitude of 12,500 meters. To accomplish this, it has 3 sea-level Raptor engines. Sea-level engines have much smaller nozzles than vacuum engines. You can see the comparison here. Here we go. The Starship lifts into the sky slowly, burning a little more than 2 tons of fuel per second. It rises higher and higher, speeding up as it gets lighter, because the thrust of 3 engines can lift the ship faster as the methane and oxygen levels drop. The 3 engines are burning through 120 tons per minute. Now, the density of liquid oxygen at cryogenic temperatures is about 1.25 tons per cubic meter, and methane at cryogenic temperatures is 0.424. It turns out that you need 4 times the mass of oxygen to methane because CH4 plus 2 O2s equals 2 H2Os plus CO2. Carbon has an atomic mass of 12, oxygen 16, and hydrogen 1. So methane has a total mass of 16, diatomic oxygen has a mass of 32, and it takes 2 of them. So we're looking at 16 to 64, which is 1 to 4 by mass, methane to oxygen. Now we see that the oxygen is a lot denser than the methane, about 3 times as dense. So the mass ratio is 4 to 1, while the density is 1 to 3, giving us a tank size ratio of 4 to 3, meaning the oxygen tank will only be 33% larger than the methane tank. Here you can see a beautiful cutaway of the Starship rendering by Neopork. His art is some of the best available anywhere. Follow him on Twitter to keep up with his amazing work. Now, SpaceX has not given us the takeoff mass, but I've watched the video and calculated the fuel needed to perform the flight, and I came up with 381 tons of fuel. I'll show you how I got that. The dry mass of Starship is 120 tons. Added to our estimated 381 tons of fuel, our total mass is just a little more than 500 tons, or 501,400 kilograms. The force of gravity on Earth is 9.81 meters per second. The Starship is pushing down on the Earth with a total force of 4,918,734 newtons. Since our 3 engines working together can produce 6,600,000 newtons of force, that gives us a thrust-to-weight ratio of 1.34. Most rockets run at a 1.5 ratio, so we can expect a sluggish liftoff, which is what we saw. Now at this point, the Starship has lost enough mass that it can shut down 1 engine, as the ship is light enough from burning propellant that it can get by fine with 2. If our calculations are correct, the ship has burned a total of 208 tons of mass and now has a mass of just 293 tons, down from the original 500 tons. The 2 engines are producing a total of 4,400,000 newtons of force, and the ship has momentum, but we can definitely see it slowing down. Everything has to be timed exactly right to get Starship to stop at 12,500 meters altitude. Now remember, this Starship has 3 sea-level Raptor engines and just enough power and fuel to go to 12,500 meters, come back and land. This means that a fully fueled Starship could never lift off with just 3 engines, but it's not expected to. For orbital missions, it has the Super Heavy lifter to take it most of the way into orbit, then it has 3 vacuum Raptors to make it on into its expected mission orbit, and 3 sea-level Raptors to come back and land. SpaceX tells us that a fully fueled Starship would have 1,200,000 kilograms of fuel, giving it a gross mass of 1,320,000 kilograms, or 12,949,200 newtons, pressing down on the Earth as it is ready for launch. For a safe 1.5 thrust-to-rate ratio, we would need 19,423,800 newtons of thrust. If each Raptor could put out a maximum 2,200,000 newtons thrust, we would need at least 9 Raptors total, with a little safety margin. This means the Starship could probably just barely get itself to low Earth orbit with no payload and 9 Raptor engines. For point-to-point travel with a ballistic trajectory, we could load less fuel and need less Raptors. Now, I understand that the weight of the Raptors has to be considered also, so our margin would actually be a little slimmer. I hereby predict that the point-to-point Starship's version will have at least 6 Raptors to produce 13,200,000 newtons of thrust, giving a 1.5 thrust-to-weight ratio to lift a total mass of about 900 tons to the other side of the Earth in about 20 minutes from liftoff to touchdown, landing with a lot less than 900 tons because of the propellant burned. Finally, after burning these two engines for about 90 seconds, they shut down to one. At this point, those two Raptors should have burned another 122.4 tons of propellant. Now this one lone Raptor, number 42, having burned continually for 192 seconds, burns for another 75, climbing very slowly and moving us out to sea a little bit in case things go bad. Now let's pause and do a little math. Remember that force equals ejection velocity times mass propellant flow. Ejection velocity can be calculated from the specific impulse by multiplying specific impulse by Earth's gravity, which is 9.81 meters per second squared. The Raptor engines have a specific impulse of 330 seconds at sea level, which is definitely where Boca Chica is. So 330 seconds times 9.81 meters per second squared gives 3,237 meters per second. We see that the thrust of a Raptor is 2,200 kilonewtons maximum. Most rocket engines operate at around 80% full power, but this is a test flight where you try to break things. Let's assume that all three engines will operate at full power. So 6,600,000 newtons is the maximum force produced by all three of these engines working together. Now, if we want to know how much fuel is consumed, we can recall that force equals propellant exhaust velocity times mass fuel flow. That means mass fuel flow equals force divided by propellant exhaust velocity. So we end up with 2,200,000 newtons per engine divided by 3,237 meters per second to give us 680 kilograms per second per engine. With three engines firing, we will start off burning 2,040 kilograms of liquid methane and liquid oxygen per second. That means our ship will be losing a little more than 2 tons of mass per second while it burns all three engines. Then it shuts down. And the Starship falls, as it is designed to. It uses its flaps to put the broadside toward the direction of travel. You will see the flaps making adjustments. Remember, air resistance is directly proportional to the area presented by the object moving through the atmosphere. The Starship has an area of 254 square meters pointing straight up and about 850 square meters broadside. That's a big difference. It falls like a skydiver and reaches a terminal velocity of 200 miles per hour. This terminal velocity will be the same whenever it is landed on Earth, whether from orbit, the moon, or Mars. Now, landing on Mars will be different. With a much thinner atmosphere, it will be more dependent on propulsive landing to survive. But Mars' gravity is lighter, so I'm sure they'll work that out. Here we see it fire up two of the engines and start to flip and land. All was going perfectly to this point, but now we start to have a problem. Let's analyze it. The header tanks, seen here and here, have the fuel and oxidizer to land. The oxygen tank appears to have been okay, but the methane tank did not have enough pressure inside to move the methane fast enough. The Starship uses autologous pressurization, meaning methane is heated and pumped into the main and header methane tanks to keep them pressurized, and oxygen is heated and pumped back into the main and header oxygen tanks to keep them pressurized. The methane header tank did not have enough pressure. The methane didn't move to the engine fast enough. The extra oxygen created a blowtorch-like effect that started burning some of the engine metal, creating this green flame. Many people familiar with rockets thought the lovely green color was due to trying to restart the engine with triethylborane or triethyl aluminum, which also burns green. But while these are used on the Merlin engine to start it, the Raptor engine uses spark igniters like a giant spark plug in a car. Without enough methane to power the engines, the Starship lands, so to speak, at about 110 kilometers per hour or 70 miles per hour. Welds break, and the ship comes apart. I'm sure you've seen where most of the media crowed the Elon Musk $410 million spaceship blew up. I don't know why schadenfreude is such a strong emotion in human beings. In truth, this is a $5 million test device producing enormous amounts of critical data. It is, in fact, a perfect test. If serial number 8 had survived, what would they have done with it? These early ships are built to be tested so we can learn all the failure points. Now, thanks to serial number 8, we've found out that everything works great except the pressure management in the header tanks, which will have to be improved, and we'll have to not land at 70 miles per hour, or everyone will need a lot more than a seatbelt. It looks like they got serial number 9 upright after a support collapsed, and I look forward to seeing it fly soon. Thanks for listening. Don't forget to like and subscribe. A little tuition at patreon.com/Terran Space Academy is voluntary but greatly appreciated. At Astra Pro Terra, stay safe.